Hey everyone, and welcome back to The Explainer. I am honestly so pumped to dive into today's topic because, well, it really feels like we're living right on the edge of a sci-fi movie. We're talking about AI agents, and not just your everyday helpful little chatbots that give you a pancake recipe. No, we're talking about autonomous systems that are actually deployed out in the wild doing real heavy lifting production work. But here's the catch. While the upside is huge, letting these systems run loose in reality is incredibly high stakes. So let's jump right in because what we're unpacking today is absolutely fascinating and, to be completely honest, a little terrifying if you're the one signing off on the cloud computing bills.
Imagine opening your laptop and staring at a surprise cloud bill for $47,000. Yeah, 47 grand. That is a completely staggering amount of money, right? Well, according to our source material from Revenium, this is exactly what hit a single engineering team over just a few short weeks. They pushed 4 AI agents into production. Week 1, super normal. Their cost was a very reasonable $127. But by week 4, the damage had literally exploded to $47,000 before anyone even noticed.
And this perfectly highlights the core problem we're looking at today, because that 47 grand bill, it wasn't a standard software bug. It wasn't some hacker exploiting a backdoor. No, it was literally just 2 AI agents stuck in an endless, completely unmonitored conversation. They were just chatting with each other in an infinite loop for 11 straight days. That is the wild new reality of agentic AI. You see, when agents talk, every single interaction costs money. And unlike the old days of deterministic software, these systems are probabilistic. So to really grasp how a meltdown like this happens, we have to look under the hood at how these agents are actually built. Okay, let's get right into Section 1, the Perceive, Think, Act loop, basically agent loop basics.
So what actually separates an autonomous agent from the AI models we mess around with every single day? It really comes down to the architecture. Your standard stateless chatbot is super simple. You send a prompt, it spits out a response, and boom, it's done. It has literally zero memory of what came before unless you specifically remind it, and it has no way to take action in the outside world. But a stateful agent, that's more like a really proactive worker standing in front of a whiteboard. It observes its environment, thinks about what it needs to do, takes a real action, looks at the result of that action, updates its whiteboard, and then loops right back around to decide its next move. It's continuous.
Let's break that loop down just a little bit further. The most common framework you'll see for this is called REACT, which stands for Reason and Act. Step 1, the agent generates a thought. It actually writes out, in natural language, its reasoning and intent. Step 2, it takes an action, like calling an external tool, maybe a web search API. And finally, Step 3, it makes an observation, analyzing whatever result came back from that tool before going all the way back to Step 1. It's this constant, rolling cycle of planning and iterating. But what actually powers this entire cycle?
That brings us to Section 2, the 4 pillars of agency. These are the core building blocks. Think of this as the engine room of the agent. Before you even start messing around with frameworks like LangChain or CrewAI, you've got to understand these 4 components identified by the dev community. We're talking memory, tools, planning, and execution. Imagine you build a real estate bot to look up housing prices in Dubai. Well, it needs tools to actually search the live web for property listings. It needs planning to logically reason that, hey, I should probably check the user's budget before I start searching. It needs execution, which is the actual code running the loop in the background. And obviously, it needs memory to remember that the user already mentioned they only want a 2-bedroom apartment. And memory is an absolute game changer here. It's not just one big bucket. Think of it more like a massive filing cabinet with different drawers. You've got working memory, right? That's the active conversation happening in the moment. Then there's episodic memory, which stores organized summaries of past interactions so the agent doesn't keep making the same mistakes. You also have semantic memory, which acts as the agent's factual domain knowledge, like knowing local real estate regulations. And finally, procedural memory. Those are the underlying execution rules and model weights that govern the agent's actual behavior. When all 4 of these pillars are perfectly tuned, agents are incredibly powerful. But what happens when they aren't?
Let's look at Section 3, when agents go rogue. This is where we get into those real-world failures. So let's circle back to that 47 grand nightmare we talked about earlier. Prepare yourselves, because this statistic from Fiddler AI is pretty jarring. They estimate that between 70 to 95% of enterprise agents, so we're talking an 85% average failure rate, completely fail when they're taken out of safe, controlled demos and thrown into messy, real-world production workflows. Bridging that massive gap between a flawless demo and a live disaster, that is the biggest headache in enterprise AI right now. And these aren't just simple syntax errors. We're dealing with really complex, probabilistic failures. To fix them, we really have to understand how they fail. Prompt metrics highlights this very specific and frankly terrifying failure mode called a denial of wallet attack. Look, in normal software, an infinite loop just hangs a thread, maybe crashes a server. Annoying, sure, but in an agentic system, an endless loop is an active financial crisis. Because agents are goal-driven, if they hit a wall, like a confusing API error, they don't always just give up. They might aggressively retry that action 50 times in 60 seconds, trying to brute force a solution. The agent literally treats your budget as an obstacle to its goal. It has no idea it's burning through thousands of dollars. It just wants to finish the job.
And then it gets even crazier. Neural trust and prompt metrics describe this phenomenon called an agentic civil war. This happens in multi-agent systems when two different bots have conflicting instructions. Picture this. You've got a security bot, and its job is to lock any suspicious accounts. Then you have a support bot, and its entire goal is to resolve user tickets by unlocking accounts. If they cross paths, you get a total deadlock. The security bot locks the account, the support bot immediately unlocks it, the security bot locks it again. They will sit there playing a digital tug-of-war, incinerating your money while your engineers are fast asleep. And the worst part? Standard monitoring tools just see all this happening as high activity and assume everything is going great. Okay, moving to Section 4, guarding the agent economy. Let's talk about creating some much-needed safety nets. So how do we actually stop this automated chaos? We've got to move past just staring at the mystery of these failures and actually master how to fix them. The Open Worldwide Application Security Project, or OWASP, points to excessive agency as a massive vulnerability. Basically, it boils down to giving agents tools they really don't need, permissions to delete stuff they shouldn't even touch, and the autonomy to just act without asking a human first. And you can't fix what you can't see, right? Standard DevOps tools might look at an agent firing off 50 API calls, see a bunch of 200 OK status codes, and be like, yep, looks good. No, we need a forensic glass box approach here. We have to be able to see the agent's reasoning trace, track its token consumption, and monitor its tool outputs in real time. So, what does a real actionable safety net look like in practice? First off, implement hard turn limits, also known as a time to live, meaning if the agent hasn't solved the problem in, say, 10 steps, just force it to stop, cut it off. Second, build agentic circuit breakers. You want something that immediately trips and pauses the whole system if it detects a loop. Third, mandate task ID deduplication, so your agents don't accidentally process the exact same request twice. And finally, you have to design human-in-the-loop copilots. At least to start, force the agent to route the really high-stakes decisions, like deleting database records or making actual purchases, to a real human being for approval. All right, I want to leave you with one final provocative question today. As we keep building out this wild autonomous future, we are literally handing machines the power to spend real money, make huge decisions, and interact with the physical world. But when an AI agent inevitably gets confused, trips into a loop, and makes a $47,000 mistake, who actually foots the bill? Is it the developer who wrote the prompt, the provider hosting the LLM, or the enterprise that deployed it? Figuring out accountability in this emerging agent economy is absolutely the next great frontier. Thank you guys so much for joining me for this explainer. Keep learning, stay curious, and I'll catch you in the next one.